Okay, welcome students back to 6.3. Let's go ahead and get started here. Okay, so we're gonna, let me share my screen. Okay, so 6.3 is on solids of revolution, but
I'm sorry, Mr. Hilton. Before we started, I was just gonna ask, did you want us to speak so you know we were here, or we just gonna get right into it?
yeah, I'll take attendance at the end.
Okay, thank you.
Okay, 6.3 is on cylindrical shells, solids volumes by cylindrical shells. Okay. Well, let's cover that. So the main idea here for cylindrical shells is this, is if I have a curve, okay, and I want to revolve this curve about the y-axis, then I can think of this as little strips, okay, that are getting revolved around about the y-axis. Okay, where the height of this strip, okay, is f of x. Okay, and the length of this strip is what we would call delta x. Okay, and that delta x is out a radius, okay, of r. Okay, so, and then we just continue to add up all these little strips, and what these create are, these are going to create areas, okay, of strips or surface areas of a cylinder. And then we're just going to kind of add up all of those cylinders. If I had another strip out here, okay, of delta x, that would be out a different r, okay, it would be out a different r, which is really the x value, okay, the radius, okay, would be out, maybe we'll call this r1 and this r2, okay, that would be out r2, and then that would create a different surface area that is a cylinder, okay, so, and so we build kind of these cylinders of with delta x, and so it's kind of the surface area of those cylinders. And if I unwrapped this, okay, these cylinders would have a certain height h, and that height h is the f value or the function value. Oops. Okay, the function value at that x, at that r value, we'll call that the radius value, that r value, or which is really an x value. Okay, so to be out here, this would be f of, say, r2, right? That would be the height of that cylinder. But we're really just looking for the surface area of the cylinder. So if I took a soup can, okay, a can of Campbell's soup or whatever your favorite soup is, Progresso, or whatever. So if I took a soup can and I cut the label off, slice the label right down the center of the soup can, okay, I would end up with a label that is unwrapped, and it would create a rectangle. It would create a rectangular area, okay? And what would the height of that rectangle be? Well, it would just be the height of the soup can. Okay, but what would be the base of that? Well, the base of that is going to be 2 pi times whatever the radius was, okay, of the circle, right, of the cylinder. So 2 pi r is the width of the soup can label, right? Maybe we'll say this. Campbell's, okay, clam chowder. Okay, whatever your favorite soup is. Okay, so Campbell's clam chowder there, you know, has an area, a surface area, okay, of 2 pi r h. Okay, that makes sense? Okay, because the circumference is 2 pi r. Okay, and that's the perimeter around the cylinder. And if we slice this guy, okay, then the circumference just becomes the top and bottom of the label. And we know that the area of a rectangle is just base times height. And so this is the base, and this is the height. Okay, and that's the area. So that's the surface area of a cylinder. So we're going to take this idea of surface area of a cylinder, okay, and we want to utilize it for volume, to find the volume of this solid that's going to be revolved. But it's going to have all these little, say, delta x's, okay? And so the volume is going to be 2 pi r h times all these little delta x's, these little widths, right? And so those little widths are going to create a volume that creates kind of a third dimension, okay? Because if we have a width here for our soup can label, if we have a defined width for our soup can label, then that creates a third dimension, and that would give me a volume. Okay? And so this third dimension is my delta x. Okay, but what is with the power of calculus? The power of calculus is that we can let delta x go to 0 and create a limit, and this will give me the exact volume. And so we don't have to have like these delta x's be like every centimeter, okay, of you know, depth. We'll call that depth, the delta x. Okay, it wouldn't be every centimeter or even every millimeter. It would essentially that width would go to 0, and so we would get an infinite number of sheets of surface areas, an infinite number of sheets of surface areas, and that would calculate the exact volume of rotating this entire figure, okay, 1 revolution. Okay, so it's a little bit more complicated of an idea, but it leads itself to helping us calculate things that weren't as easily able to be calculated with the disk or washer method. Okay, and so the calculus, how we write this is we say, well, the radius is x. That's how far out we go. And the height is my f of x. And these are things that are going to vary. That's why we call them variables, because they vary. Okay, and we're going to say that our volume is equal to 2 pi times my radius, 2 pi h delta x. But now we're going to use calculus to integrate all of these infinite surface areas. We're going to say, well, this is going to be the integral of this stuff. Well, this is going to be the volume is equal. I'm going to pull the constants out in front. That's 2 pi, okay, from a to b. I can have my limits there. A to b, what was h? H was f of x. Okay. F of x, and then what's h? What's r? R is x. And then what's h? H is f of x. And then what's delta x when we take an integral? Now it just becomes dx. Okay. And so that is our formula for the volume of a solid revolution. Okay, volume of a solid revolution okay, using cylindrical shells. Okay. So this is called the method of cylindrical shells. Okay, number one. Find the volume of a solid obtained by rotating the region bounded by y equals 0, which is the x-axis, and y equals 2x squared minus x cubed, okay, about the y-axis. And I really like the y-axis when I have a function of x, okay, because this method lends itself nicely to the y-axis, okay, especially when I have things solved for y. Okay, so I kind of as a rule here. Well, I'll talk about the rule after we do this problem. Let's do the problem first. Okay, so we want this thing bounded by this kind of cubic. And if you were to graph this cubic, it would kind of look like this. It would come in, it would flat line and bounce there. It would go back up, and then it would go down. Okay, and so we get a boundary for this guy. Okay, this is y equals 2x squared minus x cubed. 0, 0 is definitely on the boundary line. We'd have to figure out where the other 0 is here. Okay, so if I say 2x squared minus x cubed equals 0, and then I factor out an x squared, I get 2 minus x equals 0. Oh, okay, so the other 0 is at 2. So x equals 0 is a 0, and x equals 2 is a 0. Okay. So those are both roots of that equation. Okay, so this is going to be at 0, 0, and this is going to be at 2, 0. Okay, so now I know what my A and B are. My A is 0 and my B is 2. Okay, so now I want to rotate this guy. I'm going to do a little slice here. I want to rotate this guy about the y-axis, okay, with using cylindrical shells, so those cylindrical surface areas. Okay, so we want to go, our volume is going to be equal to 2 pi from 0 to 2 of x, okay, yx, because that's my radius. My radius is out x, okay, and then what's my height? My height is up f of x, right? And what was f of x? Well, it's just my function here, right? 2x squared minus x cubed, and then dx. Okay, and so easy peasy. We have 2 pi, okay, from 0 to 2 of distribute the x, that's 2x cubed minus x to the 4th dx. Okay, now we just integrate. This becomes 2/4 x to the 4th minus 1/5 x to the 5th from 0 to 2 multiplied by 2 pi. Okay, so we get 2 pi. Plug in the 2. This becomes 1/2 times 2 to the 4th minus 1/5 times 2 to the 5th. Okay, and then that's minus 0 minus 0. Okay, when I plug in the zeros, those go to 0. Okay. And then, well, 2 to the 4th is 16. Divided by 2 is 8. So I know that that's 8. Okay, and then minus 2 to the 5th is 32. So this is 32 over 5. Okay. Okay. And then I get 2 pi. Okay, well, 32/5. 8 is 45ths. I know that. So this is 45ths minus 32/5. And so I get 2 pi times, this is 40 minus 32, which is 8/5. And so this becomes 16 pi over 5. So that's the volume of that one using the method of cylindrical shells. Okay. Let's go over problem number 2. Okay, problem number 2. Find the volume of the solid obtained by rotating about the y-axis the region between y equals x and y equals x squared. Okay, y equals x and y equals x squared. Okay, so we've actually seen this problem before. We worked on this problem last time, but we used the disk method. Now let's use cylindrical shells. Okay, so if y equals x squared, oops, draw a better x squared. Okay, y equals x squared, and then we have y equals x. Oops, so we get this guy here. And we want to take this and rotate it. Okay. So let's see what we do here. Okay, we're going to rotate that guy around. Okay, with respect to the y-axis. Okay. Okay. So we can already see where these are going to be equal where the points of intersection are. If I take x equals x squared and I toss x to the other side, I get 0 is equal to x squared minus x. Factor out an x, and I see that x is equal to 0 and x equals 1 are the roots of that equation. And so 0, 0 and 1, 1 are my points of intersection. Okay, so I'm going to switch colors. Let me go to green. Okay. And I'm going to zoom in here. Okay, because what do I want? I want the volume equal to 2 pi times the integral of x, f of x, dx. Okay, and I already know what my A and B are. My A and B are 0 to 1. Okay, in the x direction. So what's the radius gonna be? If I take a slice here, what's the radius gonna be? Well, it's just gonna be whatever x is.
1.
X.
Yeah, it's x. Radius is x. Okay, so the radius is gonna be whatever x is. Okay, that's the radius. The height is not gonna be f of x, because why? Because we actually have two f of x. We have an f of x and we have a g of x, right? We have
Top minus bottom.
f of x and g of x, right? And so, Han, did you say what we want to do?
I said like the height is the top minus the bottom. So
Correct,
x
yeah,
minus x squared.
exactly. Yeah, it's going to be the f of x minus the g of x. So we're going to get, basically, kind of a smaller, thinner, it's going to be the top, top minus the bottom. Okay, basically the same thing that we did before in the previous problem, except the bottom was 0, right? If we look at the previous problem, okay, what were we integrating? We were integrating this guy, right? Right, and what was our bottom? Our bottom was y equals 0. Okay, we even said that here, y equals 0. So if we take the top function, okay, minus the bottom function, but the bottom function here is the y-axis, then that's just the top function minus the bottom function. The top function is 2x squared minus x cubed. The bottom function is 0. So if we just subtract off 0, we get the entire area, and then we're going to rotate that and create these cylindrical shells. Okay. So here we want to take the area between these two curves, which is going to be 0, 1, x times this f of x is really not f of x, it's f of x minus g of x. Okay. That's really the slice, the part of that's the height of my slices. Okay, that's going to be h. Okay, and x is going to be r. Okay, so this is going to be dx. And so we're going to get 2 pi times 0 to 1 of x times f of x was the top function, which is the x, minus the bottom function, which is the x squared, and then we get dx. Now we just go through and simplify algebraically and do the calculus, do the integration. Okay, not too tough. 2 pi. Okay, from 0 to 1, that's going to become x cubed over 3 minus x to the 4th over 4 from 0 to 1. And if both methods are valid, the washer method and the cylindrical shells method, they should both produce the exact same result. And so we get, we plug in 1, we get 1/3 minus 1/4. Okay, minus 0 minus 0. That goes away. And everybody knows that 1/3 minus 1/4 is 1/12. And we go 2 pi times 1/12, that's just pi over 6. And you could compare this to problem number 5 in 6.2, and we do get the exact same result. Okay, if we look at problem number 5 in our 6.2 notes, it's the exact same result, pi over 6. I'm sorry, this is problem number 5, yeah, in 6.2. Okay, but there we had to solve for x and then use the washer method. Okay, so Peter, you read my mind. Okay, so yeah, when should you use the washer method and when should you use the shell method? That's a great question. Okay, let me tell you a general rule. This is a general rule. Okay, this is not just in general, 9 times out of 10, this will work. Okay, however, there are special cases where you're like, one is over the other one, and I have one of those special cases in the exam review, where you're like, this should be shells, but I could also do washers, and you don't really know going in which one is going to be the easier way. Okay, just because of the nature of the functions, one way could be easier algebraically and the other way could not. However, as a general rule, this is what you do. Okay, if you have functions solved for y, okay, if you have some functions solved for y, like y equals, so y equals, blah, 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 in terms of x, okay, some f of x, and something, blah, 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 some g of x, right? And they're functions of x, right? If you have functions of x, which is usually how we're given them, right? 9 times out of 10, you're going to be given y equals x cubed plus natural log of x plus e to the x to the 14th power, whatever you want, right? A lot of times you'll be given an equation y equals, right? And you're like, okay, what do I want to do here? Right? Well, if we're rotating about the x-axis, okay, if we're rotating about the x-axis, we want to use washers. Okay, if we're rotating about the y-axis, I'll put first here because it won't always work out, okay? But again, it's just a general rule. Okay? It's basically use washers first. And if you're rotating about the y-axis, what do we want to do? Use cylinders first. Okay, so if I see an equation and I'm rotating about the x-axis, okay, and I see an equation that says, oh, take this function, f of x equals, blah, 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 and I want to rotate, about the x-axis, well, that's nice and easy, okay? Because what do? I do pi times f of x squared dx. Boom, washers, done. That's about the x-axis. I don't have to solve for x in terms of y. I would only have to do that if I was rotating about y. That makes sense? Okay, and if I'm if I have the same f of x function and I'm rotating about the y-axis, okay, I would want to do my cylinders. Okay? Makes sense? So that's the default. So your first inclination would be, hey, yeah, I want to. Now, there is a little caveat, and we're going to see the caveat in the next problem, because sometimes it's easier to not have to deal with square roots, right? Does that make sense? Sometimes it's easier to not have to deal with square roots. And sometimes if we have a square root, we can square it with the disk method, and then boom, we're good, right? And we can get rid of the square root right away. But if we can't get rid of the square root, then we might want to solve for the other variable and then square both sides. So we end up with a polynomial. Okay, for example, okay, let's look at example 3 here. Okay, use the method of cylindrical shells to find the volume of the solid under the curve y equals radical x on 0 is less than or equal to x less than or equal to 1, rotated about the x-axis. Okay, so rotate that about the x-axis. Nice, 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 yes. Okay, so it's x-axis. What would be the easier method?
The washer.
The washer method.
Yeah, very good. It would be the washer method, because we would be able to square that square root and completely get rid of it. Okay. However, sometimes it's not feasible. You know, maybe this is, instead of to a 1/2 power, maybe it's to a 5/2 power or a 3/2 power or something like that. And then we have to say, okay, but the default should be, let's do this with washers, okay? Or basically it's a disk at this point, because there is no other function. Okay, it's just taking this and rotating it about the x-axis, right? Okay. So the radius is the f of x, and then we just rotate. Okay, so f of x equals radical x. Now let's do this with cylinders, because sometimes the cylinders are actually better to deal with, because it creates polynomials, and then we don't have to, in this case it's really simple, but in other cases, if we had a bottom function, it might not be as simple. If we had to do washers with a bottom function that has to be squared and manipulated, might not be as simple. Okay, however, if we are doing this with respect to the cylinder method, and we're rotating about the x-axis, we have a different formula. Our formula then is rotating about the x-axis with cylinders is this formula: 2 pi c to d of y, f of y, dy. Okay, so we just have to change our frame of reference. We have to change our default axis. Okay, so if I want to, this is to rotate about the x-axis using washers. So we just have to solve this guy for x, which is actually pretty easy because it just becomes y squared. Okay, so this guy, okay, here is now f of y, which is y squared. Okay, which is basically just a parabola flipped on its side, which is what we have. And what are we going to do? We're just going to rotate this thing. Okay, now, what am I rotating though? Well, I'm only rotating the top half. Okay, so I'm only rotating the top half. I'm not rotating the whole thing. Okay, so my limits of integration have to go from 0 to 1. Okay, so they have to go from 0 to 1 because this point here is at 1, 1. Okay. So I don't want to go from -1 to 1 because then I would get both of them rotating and spinning and I would create a double volume. Okay, get twice as much rotation. Okay, so we're going to go volume is equal to 2 pi from 0 to 1 of y, and what's f of y? Well, that's just y squared.
Y square.
Is it though? Let me think about this for a second. Because now we're, instead of going with the x, we want the height of our cylinder. So it is not y squared. Okay. We want the height of our cylindrical shells. So I'm going to create a slice here. And instead of a vertical slice, we're going to do a horizontal slice. Okay, and that slice is going to create my cylindrical shells. So I have to think. Okay, I have to think. What is the radius of my cylinders? My radius is still y. That makes sense. My radius is still y. Okay, because y is going to give me my radius. Again, these are spinning, right? These are spinning to give me my cylindrical shells. Maybe I'll make that thinner. And so we're going to create our cylindrical shells. Okay. Okay. And so my radius is my y value. Yes, that's correct. Radius, I just think of RH, right? But what's the height? What's the height that I'm getting? Well, the height starts at the top function here is x equals 1. And the bottom function is x equals y squared. That's the bottom function. So the top function is x equals 1. The bottom function is x equals y squared. So I have to do 1 minus y squared. Okay, dy. Okay, so this really wasn't f of y. This was, say, this would be f of y minus g of y. G of y okay, in which g of y would be my x equals 1, and my f of y would be my x minus 1, my x equals 1, so f of y equals 1, and then my g of y would be my x squared. Oh, sorry, my y squared. Okay, and so I would have to subtract that to get that height. Okay, dy. Okay, so now I'm going to distribute. Okay, the volume is equal to 2 pi. Okay, from 0 to 1 of y minus y cubed dy. Okay. That's good. Okay, and so we're going to integrate y squared over 2 minus y to the 4th over 4 from 0 to 1. Okay, 2 pi. I don't know at what point I should stop plugging in the 0. Probably never, because when we start dealing with e to the x's, it doesn't go to 0. But you know, you always kind of want to check to make sure that things are actually going to 0 if they're going to 0. But this should just be 1/2 minus 1/4. So this is 2 pi times 1 squared over 2 minus 1 to the 4th over 4 minus 0 squared over 2 minus 0 to the 4th over 4. Okay, that all goes to 0. And we're left with 1/2 minus 1/4. Right. 2 pi. And we get 2 pi times 1/4, which is pi over 2. And that's exactly what we got for problem number 1 on 6.2. Okay, now, which method was harder? Yeah, this one was definitely harder. Okay, the disk method was a whole lot easier. Okay, but I wanted to show that you can do it either way. It is possible to do it using disks or using shells. You just have to change, okay, your frame of reference. Let me, this is rotating with about the x-axis. Let me highlight that. Okay. So if we rotate about the y-axis, we don't have to do anything. We just use the function as it is. If we rotate about the x-axis, we have to solve the function in terms of y. Okay, f of y is g of y. Okay, whereas before, we had this guy, okay, and this is rotate about the y-axis. Just note that in your notes. You can go back and note that in your notes. This is, okay, rotate about the y-axis. Okay, this is a pretty tough concept. I mean, we've really kind of stepped up the level of difficulty in you know, right away. Okay, and so when I first took this class in college, I think I was a sophomore. I hadn't, yeah, I think it was my it was my second semester. No, I was still a freshman. So in my second semester in college, I went to a community college myself, but my second semester in college, I hit Calc 2. I'd taken Calc 1 my first semester, hit Calc 2 my second semester, and I was like, yeah, I don't know if it was just the instructor, or I don't think so, because he was a really good instructor. But there was just so many nuances to these things, right? It was like, okay, well, are we rotating about the x-axis? Are we rotating about the y-axis? Are we using discs? Are we using washers? Right? Are we, is there an auxiliary line that I have to worry about? Right? And so it became, where are the hard, fast rules? And the problem is that you have to really go back to, okay, to really understand these, you really have to go back to not so much the relying on the formulas, but relying on what do the formulas represent. And the formulas represent either 2 pi r(h) or pi r squared. You really have to go back to that, because if you just rely on the formula, like we saw in the last problem, you could get really lost, because your h could be something completely different, and your r could become something completely different based on where your frame of reference is. Are you rotating about the x or y axis? Or are you rotating about an auxiliary line? Because then that's going to change your r's and h's, and it's going to, you have to account for that. So you really want to, just think, right? So volume is equal to pi r squared times what we call dv, and then v is equal to 2 pi rh dv. Okay, and that dv just means that there's that third dimension that we have to take into account. Okay, and we're summing up along the third dimension, and that's what creates that volume. It's like layering discs, or wrapping shells, these cylindrical shells, over and over and over and over and over again, and we're building up this volume. Okay, it's kind of like 3D printing in a way, right? It's kind of like we print a disc, and then we print another disc, and then we print another disc, and 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 eventually we end up with, right, enough discs to where we actually get, some sort of cup, right, that we could use, right? But before 3D printing, I didn't really have an analogy to this. So that was kind of nice that, technology gave me a analogy to, you start with just a dot, and then you create a little circle, and then another little circle, and then another little circle, and then another circle, and you're building up these discs, right? And so you get a volume inside here. Okay, and these would be solid discs. If you wanted some sort of cup, you'd have to slice it off or something, use the washer method. And so you're not using the inside, you're only using, right, this, and you're gonna rotate that about some sort of common axis. But yeah, so, right, and you're gonna get some sort of cup. It's gonna play out nicely. Okay, and so you just 3D print these, and it's kind of like infinite number of layers that you're layering and layering on until you eventually have something. Okay. So we can either use discs, or we can use infinite discs to do this, or infinite washers. Okay, if we're punching out the middle, or we can use cylindrical shells by just wrapping and wrapping and wrapping and wrapping and wrapping. Okay, so that's kind of the concept for the difference between washers and cylindrical shells. And I didn't really catch that concept when I first took this class, which was a little while ago, probably over 20 years ago. So, yeah, so again, I try to explain that in as best a way as possible because, you know, and I've actually seen a lot of like high school teachers who teach calculus, and they really didn't understand this concept. They're like, oh, just plug it into the formula. I'm like, you really can't do that. Okay, you can't just plug that into the formula because the formula will fail you depending upon which situation you have. Okay, it's a general guideline of how to utilize these concepts of infinitesimals. Okay, we're creating infinite surface areas or infinite areas of a disk, and then we're going to sum them up. Okay, let's look at number 4 here. That's my little rant on me as a college student. Okay, number 4, find the volume obtained or of the solid obtained by rotating rotating the region bounded by okay, y equals x squared, or sorry, x minus x squared and y equals 0 about the line x equals 2. Okay, so what does x minus x squared look like? Okay, well, it's a parabola. Okay, and the roots of the parabola, okay, x minus x squared equals 0. The roots of the parabola are at 0 and 1. Okay. So x times 1 minus x, 0. So we get the roots of the parabola at 0 and 1. So x equals 0 and x equals 1. Okay, and so we get our 2 zeros there. Okay, now where do we want to rotate this figure? Okay, after we draw it, let me grab this and push it down a little. Things are kind of running together. Okay, so where do we want to eventually rotate this around the auxiliary line x equals 2, which is right here. Okay, that's the auxiliary. So we want to rotate around that. Okay, so that's nice. It is in the parallel to the y-axis. So we are rotating about a y-axis, but it's just moved over 2 units. Okay, so we don't have to solve for y in this case because we're rotating. Okay, we are going to use cylindrical shells. We're rotating about a vertical axis. Okay, and so what are we going to rotate though? That's the thing here. Well, it's x minus x squared. Well, what does y equals x minus x squared again look like? We have our roots, our x-intercepts. There is no y-intercept except at 0, 0. So 0, 0 is a point. Okay, and 1, 0 is a point. Okay, but we can rewrite this thing as y equals negative x squared plus x plus 0. And again, we have x equals negative b over 2a. Remember this time. Okay, and so b is 1, c is 0, and a is negative 1. So we're going to have negative 1 over 2 times negative 1, which is 1/2. So the vertex would be at 1/2. Okay, and so we'd end up with 1/2 minus 1/4. So this would be up 1/4. Okay, so 1/2 1/4. And that would be our parabola. Okay, so it really is this guy here. This, I'll take a slice there. Now we're revolving about that guy, and so I want to create a cylindrical shell out of this. Oops. Let me make that a little nicer. We're going to create a cylindrical shell out of this. Okay, so we have to ask ourselves, volume is equal to 2 pi RH. Okay, and we want R and H in terms of X. So where are we going with this? So what would be the radius? What would be the radius of my circle? The radius of my circle, okay, is here. This is the radius of my circle, R. So what is R though? Well, R is the difference between where I'm at and 2. Right? R is the difference between X and 2. So wouldn't it just be 2 minus X? Right? R is 2 minus X. Okay, and then what is H? How high am I? Well, that's just f of X. That's nice. So H is f of X, which is my X minus X squared. And then what am I integrating from? Well, I'm integrating all of these pieces, okay, and then revolving them. So I'm integrating from 0 to 1.
Professor, can you go over the h of the formula? So y is h equal x minus x squared. I don't get it.
Yeah, so so H is the height of my, right? The height of my cylinder, right?
Yes.
And so I want to know how am I creating these cylinders? Well, I'm just taking, okay, the height of my slice, right? Every time I do a slice here, that creates the height of a cylinder, right?
Yeah.
And what's the height? Well, isn't that just f of X?
Yeah.
And f of X was X minus X squared.
Oh, okay. I see. Thank you.
And so we have the volume is equal to this thing, 2 pi times the integral 0 to 1. I'm going to multiply this out. 2, this becomes 2x minus 2x squared. This is going to be negative x squared. And then this is going to be negative x cubed. And a positive x cubed dx. And so we are then given, let me just leave off the v for right now. Go back to red. 2 pi times 0 to 1 of 2x minus 3x squared plus x cubed dx. Now I want to integrate. Now it's just a polynomial. It's a simple polynomial. Okay, so this becomes 2x squared over 2 minus 3x cubed over 3. That's nice. The 2's canceled, the 3's canceled. Okay, plus x to the 4th over 4 from 0 to 1. So this is x squared minus x cubed plus x to the 4th over 4 from 0 to 1. Oops, already did that. Come on. Okay, 2 pi. And so I get, just plugging in 1, I'll get 1 minus 1, which is 0. Okay, plus 1 to the 4th is just 1/4. Okay, everything else goes to 0, except for that 1/4. Okay, and so this becomes pi over 2. Okay. Okay, that we'll end the notes here on 6.3. Stop recording.